Okay, so I think we're recording again. I hope so. Otherwise, I'm going to waste a lot of my time tonight. I am going to jump into some notes that I have scanned and uploaded to Blackboard. The first chunk of stuff I want to look at is titled Power Series Analysis. So we're revisiting some of the stuff we did with Taylor series, and I'm going to switch over to a PDF of those notes and kind of talk my way through them. I think this is a terrible substitute for me mugging at you and trying to keep you engaged when we're actually doing this stuff at the board, but it's the tool we have available to us. So I'm going to try to get that to work by sharing the screen I'm using and switching over to this document. All right, so power series analysis. We spent a lot of time doing Taylor series analysis previously, and when we did so, the idea was that it would serve as a useful way to force a potential energy function to look like a Hooke's law potential energy function. And then we would exploit that to our advantage and say, oh, I'm not going to calculate a complicated physical problem's dynamics. I'm going to calculate some simple approximate dynamics, and I'm going to pretend it's good enough. And it is good enough. It just works. It's a great tool. But we're going to do this current analysis to a different end. So we're not just looking for an approximation. So what I'm going to do is revisit the idea of using a power series to solve a differential equation. We haven't actually explicitly done that in this class. You should have maybe seen that elsewhere. Maybe not, but we can work through it here. It's not complicated. So I want us to think about this differential equation. First derivative of y with respect to x plus y itself is equal to 0. Or if you want to rewrite this the other way, you could say dy dx is equal to negative y. All right, so we can solve this differential equation using a series method. What the heck does that say? With the decision that we are solving in the vicinity of some x naught. Yeah, okay, so we're going to solve this differential equation problem around some point x naught, not just, in general, but in some specific neighborhood. And we're going to do so by assuming that the equation that solves this thing, y of x, has a functional form. Y of x, the solution to the differential equation, is equal to the sum of an infinite series, a sub n, these are coefficients, we don't know what they are, they're just some constant, times this quantity x minus x naught to the nth power. So x is the independent variable, right? Y of x, it's a function of x. And x naught, remember, is just a constant. It's just telling us where the vicinity of this thing is. Where are we solving our problem? Where are we analyzing this differential equation? Okay, so let's write this out. And we're going to say, for the time being, just to make doing this derivation a little tidier, we're going to say that x naught is equal to 0. Which is just a question of choosing our coordinate system in a helpful fashion, right? So when we do that, we can write y of x is equal to a naught, some constant value, plus a1. Again, we don't know what this coefficient a1 is, times x, plus a2, do not know what a2 is, times x squared, plus a sub 3, no idea what a sub 3 is, times x cubed, plus so on, higher order terms. All right, well, that's fine. I don't know what those a values are, but I sure know how to take derivatives of powers of x. So I'm going to do that. And I take dy dx by just taking ddx of all that stuff here. Just plug that into the calculation. All right, well, ddx of a naught, that's a constant, so it just goes away. ddx of a1x gets me a1. ddx of a2 x squared gets me 2a2x, right? Nax to the n minus 1. A3 x cubed, I take ddx of that, and I get 3a sub 3 x squared, plus the other stuff. It keeps going. I'm not neglecting those terms at this point. I'm just not writing the infinite series. All right, let's keep going. So I've calculated dy by dx. I did that term-wise analysis, and I had an expression for y. So not really knowing if this is going to work or not, I'm just going to go ahead and plug that stuff into my differential equation. So I'll take my dy dx that I calculated, this stuff, and plug it in here. And I'll take my y of x, which is my assumption that it just looks like this, and plug that in here. All right, so I write that out. This is my dy dx plus this is my original y of x function. All of that is equal to 0. And now what I'm going to do is I'm going to group terms that have the same power of x. So this thing has no power of x. This thing is linear in x. And this thing is linear in x. This thing has no power of x. This thing is quadratic in x. This thing is quadratic in x. I would have terms here that have an x to the third. I'd have terms here that have an x to the third. I'm just going to take stuff that has the same power of x and group it together. That gets me a1 from right here plus a0 from right here times nothing times 1 plus 2a2, that goes here, plus a1 times x plus 3a3, that comes down here, plus a3, or excuse me, no, plus a2, that comes down here. So I've got 3a sub 3 plus a2 times x squared plus all the other stuff. I am just grouping terms together if they have the same power of x. And the right-hand side is still 0. I didn't do anything to that. Okay. X here is our independent variable, which means it's tunable. You can set it to whatever value you want, and you should be able to get a value y of x. Y of x is a function, so it turns x's into y of x's. So whatever we choose x to be, we should be able to generate a y. All right, so to get that coefficient of x, this guy, or no, let's go back one step. We seem to get the coefficient of x to the 0th power, which is this one, right? X to the 0th power is 1. So to get that coefficient times x to the 0th power plus this coefficient, 2a2 plus a1 times x to the 1st power, plus this coefficient, 3a3 plus a2 times x squared. To get those individual terms in the sum to all add up to be 0, no matter what we set x to be, right? Regardless of what value we plug into x, this thing has to equal 0 on the right-hand side. So I change x, and this term changes, and this term changes in a different way, and the term that has x cubed changes in a different way. To get all that stuff to add up to always be equal to 0 is pretty much impossible unless the coefficients of each term in that sum are identically 0. So if this is always 0, this is always 0, and this is always 0, and all the other coefficients are always 0, then this thing on the left-hand side will automatically always equal to 0. So let's just assume that. a1 plus a0 is equal to 0. That is my first coefficient here. 2a2 plus a1 is equal to 0. That's my coefficient of the term linear in x. 3a3 plus a2 equals 0. That's my term linear in x squared. You can see why I missed my chalkboards already. So we're going to set all these combinations of coefficients, or all these combinations of a's that form the coefficient of each power of x equal to 0, and so on. Okay, so can we solve that system of equations? We can't completely do so because we have, if I did this in my head right, we have n is equal to infinity unknown a_n's, but we only have infinity minus 1 equations. I admit that I haven't thought about this since I was your age, so I might have to wave my hands a little bit here, but I'm pretty sure that the fundamental theorem of algebra can be invoked here to say we do not have enough equations to solve for all of our unknowns. Okay, but that's fine. What we'll do is we'll just say we will leave one of our unknowns in terms of the other ones. Or if you like, we can do it the other direction and say we'll write all of the unknowns in terms of one of them in particular. So let's say we will figure out what a0 is at some later time. Okay, that means we're going to solve the other equations in terms of a0. So that first one gets us a1 is equal to negative a0. That's easy to see, right? We had this coefficient times x to the 0th power is equal to 0. So a1 plus a0 is equal to 0. That means a1 is equal to negative a0. All right, well, we now have a value for a1. We don't know what a0 is. We're just going to say worry about it later. We'll figure out a0 later. We'll keep it as just the variable name a0. But now we know a1 in terms of a0. We're going to take a1 and plug it into the next coefficient. So we've got 2a2 plus a1 is equal to 0. Well, I can solve that, and I get a2 is equal to a naught over 2. Okay, so let's walk through this one more time. I assume that I just will figure out a naught later. And once I've made that assumption, I can figure out what a1 is in terms of a naught. And I can figure out what a2 is in terms of a naught. And I can keep going. I look at the next coefficient. 3a3 plus a2 is equal to 0. And I solve that, and I get a3 is equal to negative a naught over 6. Here's my big capitals, and so on. I just keep doing this, right? So we now have our original guess for the form of this function, a naught times x to the 0th power, plus a1 x to the 1st power, plus a2 x squared, plus a3 x cubed, and so on, has to be equal to, well, a naught's equal to a naught, a1 is equal to negative a naught, a2 is equal to a naught over 2, a3 is equal to a naught over 6. So we solved that set of equations, and in doing so, we figured out how to specify all of these coefficients a sub n in terms of just one of them, the a naught that we don't know yet. All right, then we'll factor out a naught. That leaves me with y of x is equal to a naught times 1 minus x plus 1/2 x squared minus 1 over 6x cubed, and so on. All right, does this feel like something you've seen before? Because it should maybe look like you're finding a Taylor series solution for y of x, and maybe it kind of has to look like some kind of power series solution because of the uniqueness theorem for differential equations. All right, so I can't give you an actual solution to the differential equation that we started with here. Is this a waste of time? I still have those a naught terms in there, and you know, you told me dy dx plus y is equal to 0. And I said, okay, y of x is equal to a naught times a bunch of stuff. I guess that tells me something interesting about the functional form of a bunch of stuff, but I don't know a naught, so I can't make money with this solution. I can't tell you how to calculate something useful. But this is not a problem, because if you remember how we solve differential equations with those 1,900 different arcane tricks, we had to have initial conditions, or boundary values more generally, right? We call them initial conditions if somebody tells you, oh, y of t is equal to 0 is equal to blah, 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 blah. And y prime of t is equal to 0 is equal to blah, blah, and so on, right? People will give you initial conditions, or more broadly and mathematically speaking, boundary value conditions. And then once you have those boundary values, you can solve the differential equation for those given boundary conditions. Okay, so you gave me this differential equation right here, and I got to this point. Y of x is equal to a naught times this quantity, 1 minus x plus 1/2 x squared minus 1/6 x cubed plus some stuff. And I got stuck. I couldn't go any further. And that's when I say to you, hey, you have to give me y of x is equal to 0 is equal to y naught, or some other piece of information. But let's stick with this one for the time being. You have to give me this initial condition, you know, if x is something like a time variable, or a boundary value if we want to be more general in our mathematical language. So I wring this quantity out of you, and you tell me y of x is equal to 0 is equal to y naught. And then I plug that in. Y of x is equal to 0 is equal to y naught. I got this information out of you by hook or by crook. I know that it's equal to a naught times all that other stuff, but now I'm going to plug in x is equal to 0 in all those places. And I get y of x is equal to 0, which has to be equal to y naught, you told me that, is equal to a naught times 1 minus 0 plus 0 squared minus 0 cubed plus a bunch of other zeros. So all that stuff except for the 1 drops out, and I'm left with y of x is equal to 0 is equal to y naught, and y naught is equal to a naught. Okay, so now if you've given me dy by dx plus y of x is equal to 0, and you gave me this boundary value, y of x is equal to 0 is equal to y naught, then I know that a complete solution for that problem is y of x is equal to y naught times the quantity 1 minus x plus 1/2 x squared minus 1/6 x cubed plus the series continues. Okay, what's the point? Why am I doing this? Why am I messing with these power series? The reason is because I know the rules for manipulating powers of x, right? Like, I'm great at doing derivatives on powers of x. And because I can play that game with the coefficients, that I did to figure out what the a sub n's were in terms of something else, right? I said, oh, all the stuff that's multiplied by x to the third power has to add up to something. In this case, is 0. All the stuff that multiplies x to the 75th power has to add up to something. Again, in this case, with that differential equation, it has to add up to 0. And knowing that information allows me to just knock out all those a sub 752, a sub 9, a sub 65. I can get rid of them all and put them in terms of one unknown, a naught, and then I just give you $5 and you tell me what a naught is indirectly by telling me some initial value condition. Okay, so we used a very simple differential equation, dy dx plus y is equal to 0. But this kind of approach works for more complicated differential equations too. We're going to say, oh, what if you had something on the right-hand side that's, this forcing function that drives your value of y of x? Well, take that thing and break it down into a power series in x, right? And then group all the coefficients of x to the third power together. You'll be able to make that work. Okay. There is a bunch of math that we're supposed to do to prove that all this works. And that was what my entire college education felt like, proving that the tool worked. But when you reach for a screwdriver, you rarely prove to yourself that a screwdriver works. So I guess I'm doing something that my own instructors encouraged me to do, and I loathed it. I was really upset about it when they did so, which is to say to you, this works. Let's try using it, as opposed to starting through some kind of convoluted process to make sure that we all, I don't know, have dotted all the I's and crossed all the T's in our contract with mathematics to show that this will work when we're solving those problems. So I'm not going to worry too much about proving things that go into this. I'm just going to say this is a really useful tool for studying differential equations, right? I used it for a very simple diffeq, far, far simpler than the diffeqs we were working with earlier this semester, but it was a good demonstration model. Okay, so let me go back to, my ghastly visage. Let me return to that. That is a revisitation of our en passant. That is a revisitation of our en passant discussion of how power series analysis works. We've brought it up when we needed it in the past. Usually we were building power series to do a Taylor series expansion for stuff, although occasionally I would just do it to be a curmudgeon and to say, hey, why does the binomial expansion work? The binomial approximation. The binomial approximation, I don't know why it works, but I can prove that it works by doing a Taylor series. So we have seen this stuff in the past, but I wanted to revisit it specifically because of where we're going next, which is to say, all right, well, that's a power series in powers of x. Does it only work for powers of x? All right, so I'm going to stop the video here and then record yet another exciting one, but we're going to break this into chunks. Okay, talk to you in a second.